In the last lecture, we had examined how to extend the solution that we had for a point source of heat to a distributed source of heat. Okay. Okay, if I have a point source, okay, at some location x s, okay, of strength q, and I am observing, okay, okay, and I am observing that some observation location x, okay, we had derived the solution T is equal to 4 pi k, I am sorry, okay. That was the temperature. The flux was equal to q into x minus x s by 4 pi into, okay. This, as I said, was solution of the equation del square T plus q delta of x s is equal to 0. There was a point source only at that location x s, and it was a delta function. So, it was generating q energy per unit time. Okay. There should be a thermal conductivity here. It was generating q energy per unit time, q times delta of x s, which is a delta function in 3-dimensional space. Okay. Q times delta of x s, which is a delta function in 3-dimensional space. It has the same dimension as heat generated per unit volume per unit time. We had then extended it to a distributed source, okay, a volumetric source qv of x prime, okay, and the observation point is x. Okay. X prime is the source point, the observation point is x, and from the source point to the observation point, this is x minus x s. Okay. This is x minus x s, the distance from the source point to the observation point. Okay. And in this case, okay, so I should write this as x prime. Okay, that is the vector distance. Okay. And in this case, we had a straightforward extension of this. Okay. Integral over the source locations of the volumetric source of x prime by 4 pi k into x minus x prime. Also written as integral over dv prime of g of x minus x prime, okay, times q volumetric source of x prime, a convolution integral, okay, where g is the Green's function is equal to 1 by 4 pi k into x minus x prime. Okay, so that was the Green's function. Okay. I should note here that this is the Green's function in an infinite domain when there are no boundaries. Okay, because this solution does not always satisfy boundary conditions on a finite boundary. So, there is an infinite, it's a Green's function in an infinite domain. Okay. And the flux vector at the location x, okay, this is the temperature at the location x, is equal to, okay, 1 by 4 pi integral dv prime of qv of x prime into x minus x prime whole cubed. Okay. So, these are just straightforward extensions of the point source, and we were trying to solve a problem of the heat conduction from a wire in the previous lecture. So, I will just continue that. Okay. So, what we had was a wire of length 2L, okay, going from minus L to plus L and an infinitesimal thickness. Okay. So, that it was effectively a delta function in the two perpendicular directions x and z. Okay. So, the wire was generating heat Q per unit length, okay. The heat generated was Q per unit length. Therefore, the volumetric source is equal to Q into delta of x prime into delta of z prime, because it is non-zero only when x prime is equal to 0 and z prime is equal to 0. It is 0 whenever x prime is not equal to 0 or z prime is not equal to 0, right. So, the volumetric source is a delta function, okay. And for this delta function source I had straight away applied this formula, okay, for the temperature field, okay, multiplied by the source times divided by the distance between the source and the observation point, delta of x prime, delta of z prime divided by the distance square. The delta function is non-zero only when x prime is equal to 0 or z prime is equal to 0, and the integral is 1. So, therefore, when I have an integral of a delta function times something, I can remove the delta function and the integral and set x prime is equal to 0 in what is remaining of the integrand. Okay. Similarly, that for the z direction, okay. And then you will get this expression, integral from minus L to L of Q by 4 pi k into this thing 1 by x square plus y square plus z minus z prime the whole square whole to the half. Okay. And I had done this integral for you in the last lecture. You get a logarithm of this thing, okay. So, of this argument, okay, as the integral. Okay. You can do it by substitution by taking x square plus y square plus z square plus L y minus L y minus y prime as a function w and then integrating that. Okay. I will not go into that, but I will just try to show you what happens for the temperature field. Okay. How can we check the consistency of this? Okay. Q by 4 pi k, the natural logarithm of L plus y plus root of. Okay. I will use the substitution r square is equal to x square plus z square. Okay. Rather than writing x square plus z square repeatedly, I will just use the substitution r square is equal to x square plus z square. Okay. So, this is a little complicated. I will simplify it by just taking the plane x z plane, okay, y is equal to 0. So, x y is equal to 0 z. Okay. I will just take the plane where y is equal to 0. Okay. Note that q is energy per unit length, okay, energy per unit length of the wire. Okay. So, this is the solution I get at y is equal to 0, the plane passing through the center of the wire. Okay. Y is equal to 0 is the plane passing through the center of the wire. This is the solution I get for the temperature field. Okay. how do I check if this is consistent? Okay. So, the first thing is if I consider R to be much greater than L, okay. R is much greater than L, that means that the distance from the wire is much greater than the length of the wire. Okay. Okay. If the distance from the wire is much greater than the length of the wire, I will get T at x I divide numerator and denominator by R. Okay. So, I will get L by R plus root of 1 plus L square by R square, okay, divided by minus L by R plus root of 1 plus L square by R square. A natural logarithm that I have left out, my apologies. Okay. Since L is much smaller than R, I can use a binomial expansion q by 4 pi k, okay, into L by R plus 1 plus half L square by R square, again the logarithm. And I can neglect L square by R square in comparison to L by R, okay, in this expansion. Okay. L square by R square can be neglected in comparison to L by R. Okay. And this logarithm I can write it as the natural logarithm of 1 plus L by R minus the natural logarithm of 1 minus L by R. And you know that ln of 1 plus x is equal to x plus x square plus etcetera for x small. Okay. So, I can use that expansion for the natural logarithm, and I will get q by 4 pi k into, okay, 1 plus L by R minus 1 plus L by R, okay, is equal to q by, okay, okay. This is the temperature field due to a point source of source strength 2 QL. Okay. If you go sufficiently far from the wire appears as a point source. Okay. If your distance from the wire is much larger than the length of the wire appears as a point source of source strength 2Q times L, the product of the heat generated per unit length and the length of the wire, which is 2L. Okay. So, 2QL is the source strength, the heat generated per unit time by the wire. That divided by 4 pi k is what you would get for the solution if you went sufficiently far from the wire, so that the distance from the wire is much larger than the extent of the wire, okay, and therefore, the wire appears as a point source. Okay. So, this is consistent in that limit. Okay. When you go sufficiently far away, it should appear as a point source of source strength 2 QL, and this solution reduces to that in this limit. Okay. What about the opposite limit? Okay. R much less than L. Okay. When the distance from the wire, okay, when you are sufficiently close to the wire, okay, the observation point is sufficiently close to the wire that this distance is much smaller than the length of the wire. Okay. The observation point is sufficiently close that this distance is much smaller than the length of the wire. Then what is the temperature field? Okay. Times the natural logarithm of Now, R is much smaller than L. So, I will divide the numerator and denominator by L. Okay. I will divide the numerator and denominator by L. Okay. Okay. 1 plus root of 1 plus R by L the whole square by minus 1 plus root of 1 plus R by L the whole square. Okay. And use the expansion 1 plus x whole to the half is equal to 1 plus half x plus etc. In the numerator, you can neglect R by L the whole square in comparison to 1. However, in the denominator, plus and minus 1 will cancel out. Okay. So, I will get q by 4 pi k, the natural logarithm of 4 L square by R square. Okay. Okay, which will, I can write this as natural logarithm of x square is 2 times log of x. Okay. So, this is just equal to q by 2 pi k into the natural logarithm of 2L by R. So, therefore, the temperature field goes as logarithm of R, okay, logarithm of 1 by R, which is minus logarithm of R, in the limit as the distance from the wire becomes much smaller than the length of the wire. Okay. So, if I have a situation where the distance from the wire, okay, is much smaller than the length of the wire, okay, if the distance from the wire is much smaller than the length of the wire, okay, if I look at it in the xz plane, okay, if I look at it in the xz plane, since the length of the wire is much longer, okay, if I look at it in the xz plane, okay, the wire looks like a point source in 2 dimensions because the length is much longer than the distance from the wire. So, it looks like a point source in 2 dimensions. Okay. The temperature field due to a point source in 2 dimensions, the solution for the Laplace equation is proportional to log of R. Okay. I showed you that for a point source in 3 dimensions, it is 1 over R. You can solve the Laplace equation in 2 dimensions. Okay, it is quite easy. Okay, you recall that the Laplace equation in 2 dimensions is 1 over r d by dr of r partial t by partial r is equal to 0. Okay. Okay, so that is in a 2-dimensional polar coordinate system for an axisymmetric temperature field which is symmetric about the axis. So, in that case the solution is the logarithm of r, and the general solution that we had got correctly converges to the limiting cases both when the distance is much larger than the length of the wire, so that it should appear as a point source in 3 dimensions, as well as when the length is much smaller, as well as when the distance is much smaller than the length of the wire, so that it should appear as a point source in 2 dimensions. Okay. So, these are the 2 limiting cases. Okay. So, what we have solved so far is in an infinite domain. Okay. What happens if you are in a finite domain? Okay. So, then you have to satisfy boundary conditions on the surfaces of the domain. Okay. So, let us first consider the domain to just be bounded by just a single plane. Okay. Okay. It is bounded by a plane at z is equal to 0. Okay. So, this is the z axis, x, y, the 3 coordinate directions. Okay. And let us say that I have a point source, okay, at some location, okay, which is a distance L from the plane, z is equal to 0. Okay. It is at a distance L from the plane z is equal to 0. So, the location of this, okay, is going to be equal to 0, 0, L. Okay. And let us assume that this plane is conducting, a perfectly conducting plane. Okay. Temperature far away is T infinity. This is a perfectly conducting plane. Okay. So, if it is perfectly conducting, then there can be no temperature variations along the plane. Okay. There can be no temperature variations along the plane, right, and the plane extends to infinity. Therefore, since there are no temperature variations along the plane, the temperature of the plane is also equal to T infinity. Okay. It is a perfectly conducting plane. Let me take this. If it is a perfectly conducting plane, there is no temperature variation along the plane. Okay. Therefore, there is no flux along the plane. Okay. The component along the plane of the flux has to be 0 for a perfectly conducting plane, because there is no temperature variation, and when there is no temperature variation there will be no flux. That means that the flux lines, okay, the flux lines have to be perpendicular to the surface at the plane. Okay. The flux lines have to be perpendicular to the plane, to the surface at the plane. Okay. Now, if we did the same solution that we had earlier, okay, T is equal T minus T infinity is equal to the source strength Q, okay, the source strength Q by 4 pi k into x minus xs, okay, where xs is the source location. Okay. This temperature will not satisfy the requirement that the temperature has to be a constant on the plane, or the flux lines have to be perpendicular to the surface on the plane. Okay. So, this will not satisfy that, okay, because this solution is for an infinite domain. Okay. It is not for a finite domain. Since it is for an infinite domain, it does not satisfy this condition that the flux has to be parallel to the surface, has to be 0, or the flux lines have to be perpendicular to the plane. How do we satisfy these conditions? Okay. So, I will just show you visually how it is satisfied, and then I will tell you what the solution is. Okay. I have the source here. Okay. I have the source here plus q, okay, and this is okay at the location, at the source location xs, okay. This is the source location, okay, and then I have this plane here, z is calculated from here, x and y, okay. Now, if I put a sink, okay, so this source is located at the distance L from the surface, okay. Now, if I put a sink of equal strength, okay, minus q, okay, also at a distance L below the surface, okay, at the same distance L below the surface, okay, and now there are heat flux lines emerging from the source and going back into the sink. The source and sink are symmetric mirror images about this plane, okay. Therefore, the flux lines also have to be mirror images about this plane, okay. So, the flux lines have to go like this, okay, and if they have that mirror symmetry, you can see that for this particular case, if they have that mirror symmetry, the flux lines are perpendicular at that surface, okay. So, if I remove the surface, put a sink symmetric with the surface, then the flux lines are perpendicular to the surface at the location where the surface should have been, okay. So, putting a source and a sink satisfies the boundary conditions at that mid plane. So, the solution for that in the physical half space, in this physical half space, z is equal to z greater than 0, okay. The actual domain is bounded by the plane at z is equal to 0, and it extends from z is equal to 0 all the way to z is equal to infinity. So, that is the physical domain. If I remove the boundary for the physical domain and put a sink symmetric at the mirror image location of that plane, okay, then the flux lines go emanate from the source and are absorbed in the sink. At the surface, which is the mid plane between these two, the flux lines just by symmetry have to necessarily be perpendicular to the surface, and thereby satisfy the condition that this flux lines are that the surface is perfectly conducting, satisfy that boundary condition that T is equal to T infinity at that surface. Okay. So, therefore, the temperature field in this case can be written as the sum of a source Q by 4 pi k into x minus xs, okay, minus q by 4 pi k into x minus xi. Where this is the image location, okay, it is called the image. It is the image location placed symmetrically with respect to the source location, so that even though there is no boundary, the boundary conditions that are to be satisfied at the physical boundary are satisfied by this combination of source and sink, okay. And this goes by the name of method of images. This goes by the name of method of images, okay. And you can verify that the boundary condition are in fact satisfied at the surface, that the heat flux lines are perpendicular to the surface, because the heat flux lines will be, okay, the q z, okay, will be equal to, okay, so at a given location on the surface, okay. So, let me show it for you physically. Okay. At a given location on this surface, okay, the flux line due to the source, okay, will be in this direction, okay. The flux line due to the source will be in this direction, okay. The flux line due to the sink is in the negative direction of the flux line due to the source, okay. So, if the sink at this location, the flux line has to be in this direction. Okay. Okay, because the source and sink are of equal magnitude. Okay. From the source, it will be going along the outward radial direction to the source. Okay. It will be going along the outward radial direction to the source. Okay. Along the sink, it will be coming along the inward radial direction to the sink. Okay. So, the flux line from the source will be along the outward radial direction from the source. Flux line to the sink will go along the inward radial direction, and from symmetry you can see that if you add up these two, the flux line at the surface is perpendicular to the surface, because the source and sink are symmetric with respect to the surface. So, this satisfies the condition that the flux has to be perpendicular to the surface, because the surface is conducting. You can also show that the temperature has to be a constant along that surface, okay, because the difference between these two will turn out to be a constant along that surface. This is what is called as the method of images, okay, for a conducting surface. Okay. This I showed you for a point source. Next lecture I will show it to you for a distributed source, and then I will discuss what is to be done if that surface is insulating instead of conducting. Okay. So, I will continue this in the next lecture. I will see you then.